all bigrams or trigrams or n-grams from two texts. The one belongs, the one produced by a human being and another one produced by a bot. The clusters of bot and clusters, the respective n-grams, the clusters of the bot text would be much more compact than those of human written text. And this difference is statistically significant. We can, at least for the time being, we can catch bots on this ground. If we apply fuzzy clustering, it appears that human clusters are much more fuzzy. They have much more, so to say, outskirts of the cluster than the bots one. And the third hypothesis we would like to discuss is that if we consider this text as time series, I mean that if we change each word in the text by each word in the text by its respective embedding, we may consider the text as a sequence of embedding that is a multivariate time series. And we may calculate the characteristics of this time series. One of this entropy complexity plane, I will tell in detail a little bit later. We believe that we should verify our hypothesis, that we should test our ideas on as many languages, as many language families as it possible. We have now approximately 50 languages at our disposal, and moreover, we would like to enlarge the number. So if you have some Indian languages maybe, or some other languages, please help us, lend your help to us. It would be a kind of contribution. We translate our words of all these languages, of all this language corpora to embeddings, and apply the simplest possible algorithms of cluster analysis. It's K-means, it's the Wishart clustering algorithm. The Wishart clustering combines the ideas of density-based clustering and graph-based clustering. It's C-means, you know, it's a fuzzy version of K-means, and the fuzzy version of Wishart clustering too. It's a Wishart clustering. It's, you see, we apply it to the test data, to synthetic data. It is able to distinguish between clusters themselves and intercluster noise. And what is most important, it doesn't require a priori knowledge of the number of clusters. It's important for our tasks. Fuzzy clustering relies on what is called fuzzy numbers. Allow myself to skip it. And it's not so important. And finally, in order to distinguish between the results for human written and bot generated text, we use Wilcoxon rank sum tests in order to verify it statistically rigorously. First of all, one can see, sorry, how to list it in another way. I see, thank you. First of all, as for clustering, we can see statistically significant difference in clustering results for human and bots, for human and human generated and bot, human written and bot generated texts. Bot texts are structurally simple. The clusters are more compact and groups, whereas for literature texts, the clusters are fuzzy. And when we use the simplest possible bot, LSTM text, the clusters are noisy. Entropy complexity plane. What is entropy complexity plane? If one have a time series in one's disposal, one may calculate its two characteristics, its entropy of the series and its complexity of the series. For now, it's a very efficient tool to distinguish between chaotic time series, stochastic time series, and simple deterministic time series. Actually, if our point, I mean, our two characteristic fall into the neighborhood of the apex of the upper parabola, it means that the time series in question is chaotic. If it falls into the left corner, it means that it is simple deterministic time series. And if it falls into the right-hand corner, it means that it is some simple stochastic process. You can see the two lowest figures. The entropy and complexity characteristics for a number of time series. Firstly, the blue points correspond to Russian literature masterpieces. The green points, the green discs, correspond to simple bots based on LSTM neural network, and orange points correspond to GPT-3 based bot, which is rather efficient, I should say. For me, I am unable to distinguish by myself the text generated by this bot and the text written by humans. First of all, one can see that all these texts, all this time series produce all these texts belong to a chaotic region, and it seems to me it's a kind of discovery, maybe a kind of finding by itself, that all real-world texts, not synthetic texts, are chaotic. Second, the second conclusion one can draw that so far we can distinguish between texts written by humans and texts generated by bots. You can just draw a line between points of different color using any, I don't know, any classifier, any reasonable classifier. And second one can see that the points corresponding to bots and the point corresponding to humans are close to each other. It means that at any rate, they will coincide, I don't know, in 5 years or so. I see. It is a formal results for all bots. You see, we can achieve more than 0.95 and for complexity too. So final conclusion. So far we can distinguish between human written and bot generated texts using the sophisticated mathematical techniques. I'm not quite sure that I can state the same in the nearest future. Thank you. Thank you very much.
Takes generated by bot be much more faster compared to the takes that we originally tried. Lots of grams and possibly good algorithm target, but maybe if the difference situations and down the years. For example, if you heard about block, the bot that Elon Musk has people when they are developing bots, they are trying to use different kinds of things. So, in my opinion, in coming years, maybe bots will have much more variety in a way to generate the kind of vocabulary they use. One. And the other part is the other extreme when we generate, suppose each one of us write research papers, we follow certain kind of writing style or certain kind of vocabulary. Right? So if, for each individual, if you do, you collect the text and do the vocabulary, or else you get all the documents clustered in in terms of question. So if bot can be developed to mimic someone's writing and generate some content, take content which can be attributed to someone. So in that case, it may be difficult to distinguish.
Okay, as for the first question, I could put forward two arguments. The first one, any bot, however good trained it is a trained thing, if anything, and consequently, it tends to produce, so to say, most typical engrams, the most probable engrams. And any person, any human, however uneducated he or she is, tends to produce unexpected sequence engrams. And this difference is statistically significant. So we have a hope. And secondly, I should say that GPT-3 we use 3 is very efficient, but nevertheless we are able to catch the difference. And mostly important for me is that, okay, you may train a bot to simulate, to feign a single of these characteristics. 1, 2, 3, 5 of them. But frankly speaking, besides, apart from the characteristic I have presented to your attention, we have approximately 15 other characteristics we are going to talk about for tomorrow. 15 other characteristics, and I'm not quite sure that it is a straightforward task to create, to design a bot which is able to feign all these characteristics simultaneously. As for the second, so we have a hope. And for the second question, it was about. I see. Of course, we have such ideas and we have such results, but actually, in order to distinguish between, say, writers, yes, we need a large number of texts, And sometimes it is possible if we have the respective amount of information in our disposal. Sometimes if we have, I don't know, 2 pages, it's definitely impossible.
Hello. So I wanted to ask how dependent are these methods on the structure of the language itself on which we are testing, and whether it is also effective for regional variants of the same language.
I see. As a matter of fact, we have tested it on approximately 10 various languages of 6, as far as I remember, language families. The main conclusion, it works for any human languages. But for example, it works much worse for Esperanto. You know, it's artificial languages, and it appears that it's really artificial. It's much more close to bots than to humans, despite all attempts of its creators to, I don't know, to feign, to simulate, to produce human-like language. It differs for various language families. And for me, it's even a much more reasonable classification of human languages that formal classification based on grammar or maybe origin of this as we know it now. Like this.
Thank you.
Any other comments? Okay, so let us start the speaker. Dr. Shukran, to deliver new location detection and semantic philosophy.
Oops.
You want to stand here or no?
No,
You want to one column?
prefer. If this works. Yeah, look, thank you. Sincere, other dignitaries present here. So this is a work done by my MS student who has graduated about a year back I have to come and definitely defend it. This is a problem which we have discovered as a part of a government-sponsored project. So I must acknowledge the MHRD for the interim grant and DRDO association, all that to define the problem. And the first level of this work was published in ICVGIP workshop in 21 December, if I'm not wrong. And this is sort of an end version of that. First explain what is the DL, the expansion of this is covert geolocation. And the rest of it in terms of is basically deep networks, which I'm not a very powerful person. So if you have any questions, I'll try to describe myself. But if you have any questions about hyperparameters and stuff like that, anything to do with me and my student who is actually probably Bangalore. Okay, so with respect to the support given by it, let's move forward. This is a computer vision problem, but of a slightly different nature. The world of vision has moved with supervised learning, maybe sometimes unsupervised, for detection, segmentation, recognition, classification. These 3 or 4 main tasks in vision. So whether you say segment or detect, you do for different type of objects, including humans, spaces, furnitures inside, indoor, outside, if you go various types of objects. Okay, so that's very common, but people are still another race behind to challenging new data sets to do that. We are not detecting objects like these, what you see here. Okay, so we want to go one step behind, specifically for a certain application, which I must spend time on the problem a little bit more in coming 2 minutes because it's a new type. I'm not sure. I think I'm sure that you will not be exposed to this problem. So other than objects, what do you find inside a room or in outdoor? Well, this problem is probably indoor more than the outdoor, and we'll probably talk of the application as well. So inside the room, other than objects, don't tell me that you are looking for ghosts or something like that. But let's take an application. In this, the robot vision example as an example. Okay, so robots play games and stuff like that. What if, let us say, you are interested to make a game, hopefully happily one you will have for robots doing this sort of hide and seek game like children play. Okay, small kids in their parties and all that, hide and seek, okay, or doing something like a treasure hunt. For example, you know what treasure hunt is? This is not only children, but even college guys also do that as well. Okay, imagine a robot entering this room. Imagine a robot entering this room. Okay, superpower AI robot or whatever it is. As soon as you open the door and enter inside, it's looking for something. Okay, it could be targeted. Sometimes robots have a target, but let's say it's looking for something which is the insan hideout. It's looking for places in terms of hideout. The word covert in terms of covert geolocation, which you'll find out, indicates hideout. So I'm not looking at a different application which actually triggered this problem. This is a recorded lecture live. After talking to Catherine, I can give you the driving force of the defense. But let's looking at this as a hide state game, unsupervised hideout location, location where you can actually hide things. That's what we're interested in. The moment you see that problem, because we're looking for the same device with one camera, and room layout is in theory. What can we do in terms of this? I have some diagram to illustrate what this covert geolocation is. So this is fine. You detect an object. So this is typically the camera. You do that. First, we classify these objects in terms of fears or genetic abstraction. That's what the problem here. Okay, but you can see here, this is synthetic room entering into our this. What if you want to hide something? Hide out. Behind this obstruction or behind this wall. Okay, when there's a turnaround, if somebody can hide behind this. Remember, 2D concept, but you have just one image in 2D. So you have to think of a perspective here. Explain the problem here. Around the edges are probably threat locations. Here, you can have place to hide. Also situations where there are turnaround corners, but you cannot hide something there. So that's something which you have to do for. Okay. So, So, we have to identify something like, need a little bit of 3D information structures and all that. We have used depth from a single image in our first version on the paper. Here we added some more. Yeah. So what I did was, look at the synthetic view of the surface. This is synthetic image. So there are some items in it. And anything you can go behind an object is a sort of an adversary or a threat for you in some sense for a defense application. But it could be a robot which has to go behind and look around this place to find out if something is lying. Maybe a friend or foe, doesn't matter. So if you look at this synthetic, this is probably an elevation view, if I'm not wrong with the architectural one. Let's look at the plan. So if you look at this thing the camera is down here below. And these are your objects. If these are just simple 2D diagram, now we are looking on the camera on the top, which is not available. So what are the places where people can hide or things can hide at these locations? They are not visible to them. Okay, I'll go back to that diagram here. Locations behind this, that's not visible to you. These are the locations. So, but it's okay, as long as the passive element hiding there, there's no problem, but you need to read some locations to find out where there are objects lying behind it, or they are what we call as regions of threat. So these are the corners of turnaround of certain objects where either you have to read to find out whether something is happening there, or if there's an adversary who can hurt you or can create some problems for you, actually will come out of these locations. Okay. This is a two-dimensional diagram. If you go back to the original view, this is again synthetic, taken out the floor, let's get the object. These are my CGL locations. So their edges, boundaries of certain objects, but it is at that positions where we'll receive threat locations of something, or if the robot is playing a hide and seek game, you have to reach those positions to find out the robot behind. So these are my targets. So that's an explanation of the overall problem. And this is a natural rule. This is trying to generate, this is not our work. Single view from a single image. Using that map and that. If you look at this, and we're looking at this behind this object, which is not visible in general. We didn't use this type of thing, but we want to show. If you ask me what are the locations of the CGL, I'll come back. These are could be some this one. This corner in which also is. So these are some examples of our. So we created a data set about 1,500 samples of these annotations which a machine has to detect. So these are basically edge boundaries, all right, but not all of them. I'll show examples where boundaries objects are not all the time in CGS, so the machine has to learn very carefully. And to go, so this is just a large file. Something can be hide behind these pillars, let us say, or turning corners at this point. Okay, but these are some locations very interestingly which cannot be. The green ones are actually a CGS because you can actually place an object behind, but not there because there's nothing behind it. So the red ones are not CGS because all this is around corner, but there's actually a vacuum space behind it, something will fall. This could be a CGS because somebody could be behind the state, but not here. You can't hide something behind it because the one which is. So this is something which is very interesting to find. You need a lot of observations of 3D information to get inside the system to learn it. But hopefully deep learning machines can learn all of that. That was our target. So the first version of the work, which I'm describing here, they rely too much on depth estimations, a little bit of structure to estimate. Here we pose the problem in two ways. We actually put two beautiful deep learning tasks. One is the MTL called the multitask learning. I don't have time to discuss that, but basically multitask learning is something like where you have shared features and almost similar type of task. Once we very sure that the features can be shared across two different tasks. We did that through the architecture. And the other was what is very common in detection, attention blocks. So we put attention blocks and multitask learning into our frameworks and created what we call a CGL segmentation, decoders, encoders, etc. All that. And we also found that some of these annotations are free, drawn by humans. And I was also one of the annotators, and there was no fixed size of some of these annotations. The places for CGL, they are like camera times. This is in brief. I won't probably have time to discuss much of them, but there's a shared encoder here, and there's a shared decoder also, plus there's a fusion decoder. Okay, so these are the three main blocks. Okay, where does multitask come? We'll describe it here. Where is the attention? We'll just wait for the slide. I do not have time to, but the 8020K data set, ResNet based architecture for you. Decoder basically the shared one. Then this one will be using our teaching and on model. This is where you typically have the student driving the student. This entry entry with one is in the in fact, the code is available on the shared live. So coming to the attention layer, the attention basically on here in some of the multi attention layers in this. So you talk about the attention decoder here and here as well, and the multitask learning inside the attention. This decoder that is to it blocks and not have time. The decoder provides two features of the one is the attention decoder and also provides the step where the I think this coming out in the outer this is the difference between the two. And I think it is happening here. So the digital data to be here is we can have here the program is here in terms of digital data. This is very good idea, guys. And trying to start the whole back. So this is the spectrum or the MT comes from the CGL and the FCR, the complementary one. Okay. That actually gives you here. The FC is not mentioned very easy, but probably this time. Wallet and then you have to grab. That's the automatic. Some details are in the paper, definitely. This is the one you have to the process of the art. Taking to volumes around the council. Details after performance from class is design. I'm not mentioning it. And this is the process of the art for the I think this is here block for the FL block. That, okay. Already. So that's very good. So, there's not great amount of we have to use nothing, but we have our experiments. Then also in terms of the information mapping, we found that the arguments were tracking very good. Wrong standard machines were getting. And we found that the arguments were 90% or more. And already around 89, that would be the argument, agnostic recall. We proposed one to be close. Explained here, it's all listed in the paper. This concept here, that if you have ground and predict, how do you compute? Okay, this is a formula for trying to compute the yeah, dimension agnostic. Not the part. I think it's the digital use in our it's not completely out of the not very popular one. The new thing this person will don't do that is fine. You can behind it and the prediction will I will use both. We are just this naturally so that would be our contribution.
And we.
Yeah, I think but here the result, they input the control is one. Failure for okay, then this is the secret of the multitasking. So we don't have only one. The boundary bound is the ground, and this is our result finally. This is the almost not very also falling and improving this a couple of years back. Yeah, moved done. These are proposed work. So we have to compare with that. There was no CGL database to actually compare. These mobile to these are very popular those days. I'm talking about around the pandemic time, good segments. Our block values we have so that we have this is the last one branches of the solution architecture in the multi-task plan. I think this is, as you see, one of the small benefits. So, we are discussing the task plan to extract features, and facilitate robust training with the combination of the factor. We also have features information plan, which is based on multi-layer, multi-gate attention. So there are two different stuff. Multi-task will combine multi-layer. I think our knowledge, that it is good to combine that. And of course, we use the this good that video. The video, you can nothing of something in mind. You have object and objective to turn around the there. Yeah, that's the view is moving, that's what it has on red. Basket. That is done, almost the last slide. Hang on, it's a problem often the videos. Yeah, that's, I'll keep the videos running while I have the list of references. Thank you. Yeah, questions, please.
You were that the person is sitting or standing on the floor. So the video that is not too clear. Even the distance can the sitting and then
In this last video, this one, you have to make the video roll, right? This one? Here? No, there is not the place for that. Take it from me. This is my own lab. It's not like a heavy enough clothing and it's not I'm leaving you to the yeah, so when you think that actually you think because we think in our video captured in inside the building, offices, labs, sometimes houses, collected out of video, we have to change the level. So I have to oversee and out of whatever you think you can have, okay, it's not entering the room from that way, you can do it here, you know, the stairs, but you can't have it here. You get my point? You can't have it here unless you're thinking of your eyes, which could be hazardous to think of a robot or human being, you think can't hide here and there. That's what we kept in mind when we were wanting. Come back here. That was the lines. This was the best example too. Yeah, I think I had less time. This one. Top one. Yeah, but we have the correct one because the platform for people to do that. We have this quality. We know that. You leave that in you have and you need to have this is a possible demonstration. You know, there's some of the ground we're taking around this that's what we will take over. This vacancy is related to let me, but it's never good. But it's always point about. Some of the derivation that we still- No, first of all, the annotation must be correct, because if you're teaching long. It's the first generation. Yes, any other, sorry. Thank you very much.
Speaker today is Dr. Roshin Local. He's going to talk about search. Application
143.
device constraints. Constraints are very neural architectures. Is the name like presented?
Yeah, I'm Moshin.
Yours.
Hi. Just a second. Hello. Yeah. Good afternoon, my fellow researchers. So I'm Oshin from Indian Institute of Technology, Delhi. I'm privileged to be here. So I thank my co-authors and my collaborators. So I'll start off with an introduction to manual architecture designs, followed by the traditional neural architecture search and its challenges. Then I'll move on to the hardware-aware NAS, and finally go on to have an in-depth discussion about the proposed method. So as we see here, this is a typical architecture for image classification. Now, such a model in recent times needs to be fed to these edge devices, because we want our model to run infer on these devices because of privacy constraints, and we wouldn't want to take up bandwidth, and often due to interrupted network connectivity we lose connections, and we would not want to rely on cloud-based computations. So these edge devices uh, have certain constraints, constraints, like the floating point operation constraint, or or in terms of the storage space. So certain previous approaches use pruning methods or simple manually designing architectures of smaller size by removing layers and neurons. But it has to be done for each device, taking into consideration the constraints, which can be computationally expensive and time consuming. And also it would need a human expertise. So there's a need to automate the manual architecture design process. Hence comes the traditional neural architecture search, where given the task and a set of operations, and also the number of layers or nodes, such a method arranges these operations in some sort of configuration to get the best performance for the given task. Now, a traditional, so NAS can be, NAS is, the method depends on, uses various techniques like reinforcement learning, evolutionary method, and differentiable method. So I focus on differentiable NAS. So such a differentiable NAS method has two phases, typically has two phases, the search and the evaluation. But the search process, given a task, gets the architecture, and in the evaluation phase, the architecture is further trained or tuned to get the final model, which can be inferred on an edge device. So the traditional DNAS has an element called the search cell. These search cells can be stacked to get the final model. Now, this search cell has an input, like each cell has an input 0, and the subsequent activations denoted here as 1, 2, and 3. And each of these consecutive nodes have certain lines or edges, where each line may denote an operation. And what we do is we use all the operations in the given set to act upon the given input. And the weights of the operations are the softmax of alpha, which is the architecture parameter. So we learn the architecture parameter along with the model parameters of the given operations in a bi-level optimization fashion. To do this, the training data set is split further into two parts, validation and the train set. During the so we minimize the validation loss and find the optimal alpha, that is the architecture parameters, and using the training partition, we optimize on the weights of the operations. But such traditional DNAS often focuses on uh, getting the most efficient architecture, and the focus is not on getting uh, the a model which is really specifically designed for an edge device with certain constraints. So comes the hardware-aware DNAS, where certain methods like the one cited here, proxyless NAS, adds a regularizer in terms of latency or the number of parameters, model parameters, and uses a scaling factor to tune and adjust the loss and the model size. So this scaling factor often needs to be tuned, and the search time reported is much higher. So now coming on to the proposed method. So given a set of operations, the architecture space consists of all the configurations possible with these set of operations. And given a task, we reformulate the objective function and include by including the device constraint. Here, KS denotes the search constraint, which is computed during the search process, and KD is the device constraint of any of the device we are concerned about. So in our method, we update the architecture parameters alpha and the model parameters simultaneously as shown before. Also, we update the Lagrange multiplier lambda here, which weighs the um, constraints. So a certain problem that was seen in this process was in the search phase, the calculation of the parameters or the architectural metric that we use, that is either the memory or the flops, is different in the search phase and the evaluation phase. In the search phase, we multiply the number of parameters with the softmax weight of the architecture parameters. Hence, it is different. So we give a tighter bound here. So instead of the device constraint, we have a search constraint. So we systematically make a lookup graph. We vary the search constraint within suitable bounds and find and use our search method to yield models. The final size or the flops metric reflects the device constraints. So we reformulate the objective function to include the search constraints instead of the device constraints. So we have evaluated our method on several data sets. One is CFAR 10, where we sweep across various device constraints and get uh, architectures using our method. These have been plotted with blue dots signifying a model with the corresponding accuracy and the number of parameters. Now, when comparing it with PyramidNet, which is a manually designed network, we see that our methods with 15x smaller models can yield similar performance. We've also compared it to the popular NAS method DARTS. Comparing on tiny ImageNet, which is a smaller version of ImageNet with downsampled images and lower number of classes, we see similar performance. We see a 6x reduction in size over the manually constructed ResNet variant. Also, in comparison to DARTS, we see that we can compress much further without losing accuracy. Similarly, for ImageNet 1K, our models, the search models with our method, yield slightly higher performance than MobileNet and other NAS methods like proxyless NAS. Now, our results on CFAR10 with model constraints to match the other models that we get with other previous approaches, we see that our method takes much lower search cost. It is 2 to 4% better than manual architectures like VGG16, PyramidNet, and such. And in comparison to the recent NAS method called Shapely NAS, published in CVPR last year, we see that our method takes around 1/5 the search cost. We see similar speed up in search with ImageNet 1K, but the previous methods might be similar in comparison or sometimes 1% better, but they lack the capability to search device-specific models. Now, our techniques use certain algorithmic augmentations to reduce the search time. One is weight sharing, where um, taken from the observed from non-parametric operations, where working on an given input, it irrespective of the output node, it gives similar activations. So we take this observation and use it for parametric operations here, like separable convolutions and others. We see that when we use weight sharing onto darts, which is a previous NAS approach, we see that there is significant reduction in the search time owing to the usage of larger batch size. We can use larger batch size because the memory overhead decreases, hence the search time decreases. Similarly, there's the popular method of channel bottlenecking, where we use 1x1 convolutions to reduce the number of filters. So when we use this in our search cells, we can further reduce the memory overhead and increase our batch size. And the last augmentation is the use of derived cell. So instead of using the search cell, we use the derived cell alternatively. So this cell is engineered to have only one edge between nodes. This edge is selected based on the architecture parameters. So the highest architecture parametered operation is chosen in the edge. This again decreases the number of weights and alphas, the architecture parameters to learn, hence reducing the memory overhead. And thus we can use higher batch sizes. Now, the use of resource constraint does not lead to any significant increase in search time, which is a benefit here. So we have also, thank you. So we've also tested on a benchmark, the NAS Bench 201, which has a slightly different set of operation space. And they also have a benchmark on certain edge devices, the latencies on Raspberry Pi and Pixel 3. So when we ran our method with different flops as constraints, we saw that the models that we got had significantly lower latency than what we can achieve with PC darts, another popular NAS method. So yeah, we tested on CFAR 10, CFAR 100, and ImageNet 16120, which is again a diluted version of ImageNet. So our contribution are listed here. So we require minimal hyperparameter tuning, our search is faster, and we have extensive experimentation. Concluding, our search costs are around 4 to 17 times lower than prior methods. It discovers 10 to 15 times smaller models than manually designed architectures. And future direction can be to generalize to any future updates to NAS, and then possibly adapt it to training-free NAS methods, which are emerging, and they need much lower cost. Thank you. If you have any questions.
Please let us find the speaker. So, presentation of some very interesting.
Thank you.
So we now come to the final talk in this session. I invite Dr. Kamalika Bhattacharjee. Feedback, whether number-based encoding technique for effective clustering.
Okay, good afternoon, everyone present here. I am Kamalika from Department of CSC and IT Trichy. And this work is done by my master's student who graduated last semester. So this is part of his master's thesis. As he graduated, he didn't come. So I'm here. So before going to the actual work, let me just briefly talk about what motivates us. We are the group who work on cellular automata, theory work, and here it is on clustering. So what motivates us to look at the clustering problem? So when we started doing this clustering work like few years back, we looked at clustering as a problem of bijective functions. So let me explain. So if you take the whole set of objects, it can be, you can think of any clustering algorithm as a bijective function that divides the objects into some groups. These groups will be ultimately they will be related with respect to the particular bijective functions and they will form some equivalent classes. Now each of these equivalent classes will be called as a cluster. That's how we look at the clustering problem. And we used the transitions of automata, which is a reversible transition, to cluster the objects. So for example, if you look at this figure, it's showing the transitions of a particular automata where there are some cycles and each of the cycles are called as the clusters. Now, in case of reversible CA, when we took reversible CA and applied to the clustering problem, we faced one particular problem, that was our CA takes a configuration, which is, if you take a binary C, it's a bits, it's a sequence of bits. But if you take any real data set that's containing some real numbers, so how we convert it? So for that, we needed some encoding techniques. So we, for example, here I have used frequency-based encoding technique, and this, if you take the same figure that I have shown you, this particular hypothetical data objects can be clusters like this. So they form some particular, say, 1, 2, 14, 22, 50, 62, and 54. They are in one cluster, 29 in another cluster, and 17 and 5 in the third cluster. So 3 clusters are formed by the particular automata. Now, if you look at the encoded configurations, the binary strings, you can see that some objects are mapped to the same configuration, same binary string. That may be a problem because maybe the numbers that have been put into the same configuration, obviously by the function, they will be mapped to the same cluster. But actually, if you take a clustering algorithm and apply this same attributes, might be they are belong to the different clusters. So that was one problem that we faced. That was because of the encoding technique. And another thing that we have seen is none of the existing encoding techniques was not giving us good score. In terms of good score, I'm talking about the 4 standard validation indices like the Silote, Davis, Walding, Calency, Harbus, and Dan index also. I'm not showing the Dan index result for this particular case. You can see that it's not giving a very good score. Another point is none of the existing state-of-the-art algorithms are also not giving us a good score. They are still much behind the optimal score. So that leads us to think that maybe we can think of some better encoding function, encoding technique, which will help the existing clustering algorithm to achieve the optimal score and can be used to compress the dataset. You can take any high dimensional dataset that can be compressed by the encoding technique to some manageable space, and it can cluster any real data. Like it can take categorical data, which is a very difficult thing if you consider the frequency-based encoding. It's kind of messing up all information. So this was our motivation to work with the encoding techniques. These are the evaluation metrics that we have we have used in our work, and this is the implementation setup. So here in this particular presentation, I'm going to show the result of the 4 primary data sets only. And we are going to use k-means, hierarchical, DBSCAN, WARTS, mean shift, and one particular CA-based algorithm, which is based on binary CA, for comparing the results of the encoding techniques. So first encoding technique that we tried was using the existing hashing algorithms, which can compress the data. But the problem that we faced was, if it is based on the feature values, then again the same kind of problem like the frequency based can happen, where unrelated data can be mapped to the same object. So this may lead to poor clustering. So this gives us the requirement that 2 data points should be mapped to the same encoding only if they are placed in the same cluster. And obviously we need non-cryptographic hash functions, because cryptographic hash functions, they will, like, even if the objects are similar, if you make a use of cryptographic hash functions, they might go much beyond the similarity, right? So these are the particular functions that we tested. These are 32-bit output generating hash non-cryptographic hash functions. And once we use these functions, so we get a 32-bit number. But if we want to use the same number over, say, k-means or hierarchical, we need the feature values again. So what we did, we divided the numbers into some equal parts. Here we took 4 parts. So each 32-bit number is divided into 4 parts. Each of the parts will be a feature. That's how we created a new data frame. For example, if you look at this, this is a data frame. So like say the total number is 32-bit. We have divided into 8 bits. So each of the 8 bits are some decimal numbers. Now, if you look at the results of these algorithms, that existing hash algorithms, you can see there is no improvement. Rather, even the performance scores are decreasing. So obviously, the existing hashing algorithms are not suitable for our purpose. So it doesn't give a better score, maybe because it's not preserving the properties of the features. So we go for a new encoding technique. This leads us to use the Gödel numbers for encoding. If you know what is a Gödel number, you know that it's the beautiful function originally designed by Carl Gödel for the proof of incompleteness theorems, which is just like, you can say it's the first step towards disproving the famous Enskeidan's problem. So it was a very beautiful concept. And it takes, it's basically defined over the formal languages, where you can take the functions, the well-defined formulas or the symbols, and you can represent it in terms of a particular number, which we call it a Gödel number. And you can think in this way. You can take a number, say C, it's any real number, or then you can convert it into the powers of primes, sequential primes, just like say 2 power of n0 into 3 power of n1 and so on, where 3, 2, 3, 5, these are the series of primes numbers that we are to be used for every case. So for example, if you take 600, it can be uniquely represented by 2 power of 3 into 3 power of 1 into 5 square. So once we know that what are the primes that are to be used, obviously we know that we can derive back the powers also. Now, how we use it for any sequence of numbers? Suppose we are given a sequence of integers like x1 to xn. Now, the Gödel number corresponding to this will be 2 power of x1 into 3 power of x2 and so on. So by using this scheme, you can derive back the sequence of integers given also. This is the beauty of Gödel numbering scheme. Now, in case of clustering, how we can apply it? You can think like, say this x1 to xn, these are my featured values. Say I have n number of features, so each of these are the feature values corresponding to one row. Now, first I have to obviously convert it into an integer number if there is some real point that we have to remove. Then we can take the series of primes, say ith feature, so I have to take the ith prime. I have to multiply that with the previous, say, ith prime to the power the feature value. That will be the particular value for the feature. Then I have to multiply it with the previous feature's value also. And in this way, I can generate one particular Gödel number. So the whole here the scheme is you have power for every feature value. So the whole number when you are generating it's dependent on every feature. For example, if you look at this Baring data set, the first number we can convert it in this way: 2 power of 2 was the feature value, into 3 power of 77, into 5 power of 79, and so on. So for this particular sample set, this can be converted. If we take all the features, it can be converted into a series of Gödel numbers like this. Now this is one way of converting it into the Gödel numbers. Once we have done it, now our problem is whether the conversion is still preserving the properties or not. Because that was the reason why we moved into the Gödel numbering scheme. For that, we did a very simple test. This is what we did. We generated all the Gödel numbers. We just sorted it. Then we, depending on how many number of clusters we want to find, we found the gaps between the sequence of numbers. And without doing any clustering algorithm, without going through any clustering algorithm, we just took those numbers, considered that as one cluster, and the other gap that will be another cluster, and so on. And then we tested over the same benchmark validation indices. And we see that the results are actually quite close to the existing state-of-the-art algorithms. For example, here I'm showing the k-means. You can see that without doing any kind of clustering, the score is actually quite similar to what is achieved by a good clustering algorithm. Yes. So this means that our encoding technique is actually preserving the properties of the feature. Now we apply it to the real data. And for that, if it is a high dimensional data, you might be already guessing that the Gödel number, as it is taking the powers of prime, it can be a very large number. So for that, what we did, we split the features or split the Gödel numbers into some parts. So we have 3 schemes of doing it. You can think of many other schemes also. First scheme that we tried with, we split the features into the size of the Gödel number that we wanted to generate. And then for each of the set of features, we generate the Gödel number. Second is we generate the whole Gödel number, then divide it into some parts. And third was we took a window, we just moved it over the features. So say first feature and second feature that we combine create one Gödel number, then second and third that we combine creates second Gödel number, and so on. So obviously for each of the schemes, for the same object, the Gödel number generated will be different. So this is the first scheme. Here we are converting into total 3 features. So the 0 feature is combination of a couple of features and so on. This is the second scheme where we generated the whole number, then we divided. And third scheme is like this. We took a window, we just moved it over. So over some iterations, we can generate. Once we reach two features, a total of 2 features, then we stop here. So this is the scheme number 3. So we tested over them. This is the results of all our schemes with the existing clustering techniques. And you can see this is just a summary of the result. You can see this is for actually hierarchical. The SOTA algorithm that is represented here is a hierarchical. So you can see that for Gödel numbers based encoding, sometimes it is drastically improving the result, or otherwise also it is improving the result over the existing results. So for all the SOTA algorithms, it is quite improving the results, going it towards the optimal score. So this gives us the idea that that's our encoding technique that actually improves the performance of all existing clustering algorithms if the clustering algorithm is if it is able to deal with the decimal numbers directly, because Gödel number is actually a decimal number. So if your algorithm is able to deal with the real numbers or decimal numbers, it will work just fine. It will improve the score of the original data. But if it is a CA-based algorithm, that from where we started, there was not much improvement because that was a binary CA and we were converting the Gödel number again to the binary. So all the properties preservation that we have done, that was lost. So the next task that my student did, that we are currently doing also, we were using decimal CA for clustering, using the Gödel numbers as it is, and then applying it over a automata which deals with the decimal numbers. So these are the bibliography. I want to thank Professor Mihi Chakraborty, who taught us logic and Gödel number, the beauty of Gödel number scheme, and Professor Sukanto Das. And my project, ACRV, who is supporting my work, and CPDA grant from NIT Trichy. Thank you. Any questions?
Any questions or comments?
Thank you. Presentation and I have questions for you. The first one, in actual practice, it is rare case when you know the number of clusters a priori. So we have a number of algorithms that calculate the number of clusters during the clustering process. Consequently, could you say anything about how this Gödel number techniques affects these algorithms or not? It seems to me that all algorithms you have used for comparison for your simulations belong to the class that there is a priori knowledge of
Yeah.
the number.
Yeah, right.
And second point, natural questions. How much time it takes to calculate
Gödel number, it's a constant.
numbers, at least for large data sets?
It's constant. Actually, I didn't tell for the scheme that was the first scheme that I talked about, which was taking a number of features, like you fix the size of the Gödel number. For that, how many number of features you can accommodate that you take, and then you convert. That was giving us better result, and it has lowest complexity in terms of time. And another, your question, that data set that we tried, it was all real data set and all a priori information was there. It is not a dynamic data set, right? But I feel like the scheme will be applicable as like it for the dynamic data set also, because once you know the number, you can convert it into Gödel number. The scheme will work, but I didn't test it.
Which such with feature cost on doesn't what's your you see
I didn't get you. Can you please repeat?
um actually doesn't improve.
Hmm.
Can we can we have some reasonable judgment
Yeah.
about
Why it is not improved?
about
No, actually, what I have seen is for the specialty of Gödel number is it is converting into a decimal number. So it's a real number we have to deal with. And the class of algorithm that was not able to deal with real numbers, it was not giving good performance. That was the reason that I have found out, because for that it was taking binary numbers. So I have to again convert the Gödel number into binary. So this conversion is not preserving the property. That feature property, that impact is totally lost. That's why it is not giving good performance. That is my explanation that I have found out of this. Thank you.
Thank you to all the speakers and thank you, Professor Pal, for conducting the session for us. Now I would request Professor Pavitra Mitra of IIT Kharagpur to please felicitate Professor Pal with a memento. So we'll go for a break. Refreshments have been arranged outside the auditorium, and we meet here again at 4:30 p.m. for our second keynote talk of the day. Thank you.